Hi, and welcome to the seventh lecture of group theory. So, last time we had discussed when G is a group and H and K are two subgroups, we were concerned with two things. First was whether HK is a subgroup or not. When is HK subgroup? We have seen HK is a subgroup of G if and only if HK equals to KH. And the second thing which we are interested in is order of HK. So that was the last statement, and today we continue with that result. So that theorem is, and Harshita has told me that in that theorem I forgot to mention that H and K are finite subgroups. Of course, they are finite subgroups, so that is my mistake. Otherwise, we cannot talk about it is understood because otherwise we cannot talk about the order of H and K, right? So this is the theorem. So let H and K be finite subgroups of a group G, then what we have order of HK we have seen in the few examples. This is order of H times order of K upon order of H intersection K. When we list all those elements of H and K product, we have total order of H times order of K entries, but we have seen that each entry is repeated the number of times as many as elements are there in H intersection K. So this is what we are going to prove. So, and another corollary of this, as a consequence, we have very interesting result, which we are going to prove is this. Um, so that is a proposition. Let me state this before we prove this. So, if G is a group of with order of G, suppose G has PQ number of elements, where P and Q are primes. So P and Q are primes such that so they are distinct primes. So let us assume P is bigger than Q. So P and Q are primes with P greater than Q. Then this result, which is very interesting, then at most G has at most one subgroup of order P. So the largest prime, P and Q are two primes, and order of G is PQ. For example, order of G is 15, 3 into 5, two primes, 3 and 5. The larger one is 5. So what this result says, G has at most one subgroup of order 5. Suppose order of G is 10, again two primes, P and Q. P equals to 5 and Q equals to 2, 5 into 2. That then again it says that G has at most one subgroup of order 5. जो भी बड़ा प्राइम है उस प्राइम के ऑर्डर का at most one subgroup. Either there is no subgroup, or if there is a subgroup of that order, it cannot be more than one. So this is an interesting result. What we are going to prove after two lectures, that it has at least one subgroup of order P. So if you combine these two results, it will be consequently we can say that G has exactly one subgroup of order P. So this is an interesting result, and this one at most one subgroup of order P, that follows from the theorem which I have written on the top. So let us first prove this. Okay. So let me cut this and we will use later. So let me put it at the end. Okay, so now let us focus on this result first. So we start with the proof of this. So we assume first, let us consider H intersection K. H intersection K, we know intersection of two subgroups is a subgroup. If you have difficulty with that, you can try that as an exercise, very simple exercise. If H and K are two subgroups, then intersection is also a subgroup. H and K are finite subgroups, so intersection also is a finite subgroup. So identity is there, and then this identity we call it R1, and then let us take R2 and so on. Let us take Rm. So we have m elements in H intersection K, R1 up to Rm, where R1 is the identity of the group. So then order of what is H intersection K? This is M. Right. So first we fixed H intersection K has m elements. Now what we do? So first list all the elements. First list all the elements of HK with repetitions. Even repetitions are also allowed with repetitions as HK such that H is in H and K is in K. Right? So let us call this number 1. So what we do is we list all the elements. HK, how the elements of HK look like? An element of H times an element of K. So just list all them. Now we know the repetitions as we have seen in the example in the previous video. We know how many repetitions are there. Each element will be repeated number of times the number of elements. I mean, each element will be repeated as many as times as the number of elements in H intersection K. So here we show that each element is repeated m times, right? So that is our target. But how many entries are there here? HK. So there are OH times OK. Order of H times order of K entries in the list 1. In the above list, how many entries are there? Number of elements of H times number of elements of K in the list 1 with repetitions. Of course, we have allowed repetitions. We know that there will be some repetitions as we have seen observed in the last example with repetitions. So what we shall show? We shall show that each element, we shall show that each element of HK is repeated m times in the list 1, is repeated exactly m times. M is what? M is nothing but it is order of H intersection K. So that is repeated exactly m times in the list 1. So suppose we have H has, let us say, 9 elements and K has 4 elements. So what we do? A1, A2, A9 elements of H. K के elements कैसे लिखेंगे? K1, K2, K3, K4. Then we take A1, so B1, B2, B3, B4, say, let us say. So we have A1, B1, A1, B2, A1, B3, A1, B4. Then take A2, multiply with B1, B2, B3, B4. So how many elements? 36. So we list all the 36 of them. Now there will be repetitions as we have seen in the example. So if every element appears twice, that means total distinct elements in HK will be 36 by 2. That will be 18. So if every element appears thrice, 3 times, every element is repeated 3 times in the list of 36 elements, we know how many elements will be there distinct. That will be 12. If every element appears four times, then 4 times repetitions are there, then we divide by 4. So that is what we are going to do here. We have all list of all such elements product HK, where H belongs to H, K belongs to K. So there are total how many elements in the list? Order of H times order of K. But we'll show that each element is repeated of HK is repeated m times. M is nothing but exactly order of H intersection K. So we divide by that, and that is a proof. Okay, so now let X belongs to HK. Then we can write X equals to HK. X equals to HK for some H in H and K in K. Right? And now how many times such HK can be written? So for I equals to up to M, for I equals to 1 to M, take HI, take HI equals to HRI and KI equals to RI inverse K. Right? So what we have taken for I equals to 1 to M, we have defined M elements HI. How HI are defined? H times Ri. H is this. Here there is H times Ri, and Ki, correspondingly we have Ki. What is Ki? Ri inverse K. You know what are Ri? Ri are nothing but, see, they are elements of H intersection K. So why do we define like this? Now multiply Hi in Ki. So what will be H1? H1 will be HR1. H is this fixed H. K1, R1 inverse K. So multiply H1 K1. So what will be HR1? R1 inverse K. So R1 inverse gets cancelled. What we have HK. So if I take H1 K1, I get HK. If I take H2 K2, H2 is nothing but HR2. Then K2 is nothing but R2 inverse K. R2 and R2 inverse gets cancelled. So we have again HK. So then we can write. So then X equals to HK can be written how many ways? H1 K1. You can see H1 K1. This is H2 K2 also is HK, and so on. HM KM. So did you see the technique? So X we written as X in HK, we have written as HK, we have written H1 K1, H2 K2, HM KM. So M elements are there, and we made use. Once we multiplied Ri with H and Ri inverse with K, and so now if you patch them together, Hi Ki, Ri inverse gets cancelled, we have HK. So HK can be written as so many times. Even H1 K1 is nothing but HK, because R1 is nothing but identity. So E and E inverse. So this is HE. So this is nothing but H. E inverse K. So this is nothing but K. So HK is written, is also included. And then there are M distinct ways. So this means every element X in HK can be written as an element of H times an element of K. This in M distinct ways. Because all these are distinct elements, H intersection K. So we have M distinct representations of HK. Same HK can be written like this. એક વખત R1 લઈએ તો H1 K1 મળી જાય આપણને, બીજી વખત R2 લઈએ તો પાછું HK જ મળશે, પણ H2 K2 મળશે. So all these are distinct ways, M distinct ways. We want to show that exactly M ways. M we have found. Exactly M, when we can say that there are exactly M ways, if there are no more than this. એમ મળી ગયા આપણને. એક્ઝેક્ટલી એમ હશે એવું ક્યારે કહી શકાય? આના સિવાય બીજા કોઈ ના હોવા જોઈએ. So that means suppose HK can be written as some other representation, then it should be one of this. Are you following? So M distinct ways we have found to write HK. But what we will show, these are exactly the M. What we have found are the only way to write HK. There are no other expressions. So suppose HK can be written as h dash k dash. Suppose hk can be written as h dash k dash for some h dash in h and k dash in k. So what we have to show, h dash is nothing but one of this hi, k dash is also nothing but one of this ki. So this is the only way representation. So then we show that h dash k dash is already listed in the representation in, let us call it star. So we have m representations. So m distinct we already found. હવે આ m જ હશે, m से ज़्यादा नहीं होंगे. What is the reason? So suppose hk can be written as h dash k dash, then h dash k dash is nothing but it is one of this. So that is what we have to show. So that is a claim. So the claim is, again we repeat what we have written. So the claim is h dash k dash is already listed in star. Right? So suppose hk, this is our x, hk equals to h dash k dash. So this implies multiply h dash inverse on the left and multiply k dash k inverse from the right on both sides. So we collect elements of h on one side, collect elements of k on the other side. So we have h dash inverse when we multiply on the left. So then it will be this h dash inverse and h dash that get cancelled out, and here we have h dash inverse h and then k. I'm applying both step at a time. I hope you are comfortable with this. And k inverse I multiply on the other side. So we have k dash and k inverse, right? Okay, so this implies, and so, but this is what? This is an element of h intersection k. Why? The reason is left hand side is an element of h and right hand side is an element of k, h dash k dash. So h dash and h both are elements of h. K dash and k are elements of k. So k inverse k dash, k dash k inverse, and h dash inverse h, they are all elements of h intersection k because they both are same. Left hand side is an element of h, right hand side is an element of k. So this is an element of h intersection k. But what is h intersection k? H intersection k, as you see, it is this where we started. So R1, which is identity, R2 Rm. So this is nothing but let me write the rest here. So this is E equals to R1, R2 and Rm. That means that this element is one of this Ri. So this means h dash inverse h equals to k dash k inverse equals to Ri for some I. Right? So here some problem is there. What the problem is there? I want to show that h dash equals to something like this, HRI. So like this, HRI. So h dash is HI, which I want to show. There is a problem. Now if I multiply, so I get RI H inverse. So you realize I want to show that h dash is nothing but HRI, which is nothing but HI. This is what we want to show. But now the problem is H, if I multiply, I get H inverse. So what I do is I take one more step here. If this is an element of H intersection K, its inverse also is an element of H intersection K. So H dash inverse, H inverse equals to, take the inverse of this also, K dash K inverse belongs to H intersection K. But then this is what? This is H inverse H dash equals to, what about this? The K inverse inverse. So this is K, and we have K dash inverse. This belongs to H intersection K. Now we can take this as Ri. So H inverse H dash equals to K, K dash inverse equals to Ri for some I. See, now H kai side I give H inverse R side I. So now we can multiply by H on both sides. So what this will give? First one, H inverse H dash equals to Ri. So H inverse H dash equals to Ri. This implies what is H dash? Multiply by H on both sides. So we get H Ri, which is nothing but Hi. As you can see here, H Ri is nothing but Hi. And similarly here also what we have? Ki. So Ki is what? Ri inverse K. So that's what K dash. So now we apply this. So N, we have K dash inverse equals to Ri, right? And from this we want K dash. So what we do? So this implies uh, K equals to Ri K dash multiplied by K dash on both sides. And then we want actually K dash. So now multiply by Ri inverse. So this implies K dash I am writing first, and K dash Ri inverse on the left hand side if I multiply. So this is Ri inverse K, which is nothing but Ki. So what we got? So hence H dash equals to Hi and K dash equals to Ki. So this was our claim that these are the m different ways of writing Hk, an element of Hk. But these are the exactly m ways. How do we show that exactly m? Suppose Hk can be written as H dash K dash. Then we want to show that H dash is nothing but one of this Hi and K dash is nothing but one of this Ki. So it is counted here already. આના સિવાય કોઈ નહીં મળે. બીજું લેવા જશો તો આ જ ટાઈપનું હશે. So H dash K dash લીધું તો આપણને H dash K dash શું આવ્યું? H dash K dash will be nothing but HI which is already there listed for some I. Okay, so these are the m ways. So therefore, so number of, so each element is repeated. This was our claim. So each element in this list HK લીધું તો ને H no element K no. So how many elements are there? Order of H times order of K. Total entries આટલી હતી, but each element is repeated how many times? M times. So total how many distinct elements are there in this list? One. So that is nothing but order of H, order of K upon order of upon M, which is nothing but order of H intersection K. So therefore we can say by 1 order of HK is nothing but order of H times order of K. This were the total number of entries in the list, and we divide by M, which is nothing but order of H, order of K, and M was nothing but order of H intersection K. Yeah, so simple proof. Just go through it once. I hope this is clear. We'll again repeat it in the next Google Meet. Right. So as a corollary, we have very immediate consequence of this, and this will be helpful in proving the result what we said about the group of order PQ. Okay, so as a corollary, we can write, suppose if H and K if H and K are subgroups of finite group G. Now the group G itself is finite here. So G is finite, therefore H and K obviously are finite. So if H and K are subgroups of a finite group G with order of H is greater than under root order of G, and order of K also is greater than square root order of G. Suppose these conditions are satisfied, then the hypothesis is the conclusion is H intersection K cannot be singleton identity. Right? We can write like this: cyclic group generated by E, which is nothing but so both these are same. In the book, they use this notation: cyclic group generated by E. So this is the notation. It's singleton identity, right? Same. So then that means H intersection K has more than one element. Singleton identity, or that means it has one element, but it is not equals to singleton identity. That means H intersection K has more than one element. So this is a very nice statement, and it has an application which we are going to see now. What it says: if we have two subgroups H and K, both have order which is greater than root order of square root of order of G. બંને માટે order of H also is greater than square root order G, order K is also greater than square root order G. તો પછી શું થશે? H intersection K will definitely have element other than identity. Identity સિવાય બીજા element હોવા જ જોઈએ, કેમ કે મલ્ટીપ્લાય કરો તો શું થાય? સ્ક્વેર રૂટ ઓર્ડર G સ્ક્વેર રૂટ ઓર્ડર ઓફ G, which is order of G, and આપણે HK, this formula we apply, what we have seen already here. So now, so this is what we apply as a corollary, right? So let us see the proof of this. So since we know HK is anyway subset of G, because this is HK is nothing but set of element of H times element of K, H into K, and G, they are anyway elements of G. G is closed, so G is a group, so they are elements of G. So since this is the case, what we know is order of HK કોઈ દિવસ આનાથી તો વધવાનું નથી. Order of HK is always less than order of G. HK is subset of G, so the order is less than or equals to the order of G. And now suppose whatever the condition is given, so suppose order of H is greater than square root of order of G, and order of K is greater than square root of order of G. Suppose this is given. What we have to prove? We have to prove H intersection K is not singleton identity. That is, order of H intersection K is greater than 1. આવું થાય? H intersection K singleton નથી. That means order of H intersection K is not 1. It must be greater than 1. This is what we have to prove. Suppose if possible, so suppose if possible, order of H intersection K equals to 1. Suppose it is singleton identity, so only one element is there in H intersection K, which is identity, because H intersection K is anyway subgroup, so identity has to be there. It cannot be empty. Subgroup છે ને, identity આવે. So then by above theorem, what we can say? Order of HK equals to order of H, order of K upon order of H intersection K. This is the theorem which we have just proved. Now, but this is greater than, see, order of H is given to be greater than square root order of G. Order of K is also given to be greater than square root order of G. So this is greater than square root of order of G, square root of order of G upon order of H intersection K. And this is equals to order of G upon 1, because we have assumed order of H intersection K, suppose this is 1, so here it is 1. So this is what? This is equals to order of G, which is a contradiction. Why this is contradiction? Because what we have got, order of HK is greater than order of G, and what we had here, order of HK is less than equals to order of G. So this is the contradiction, right? Anyway, HK is subset of G, so it cannot have more elements than G itself. So this is a contradiction. Therefore, our assumption that H intersection K has only one element, identity, is false. That means H intersection K is non-trivial when both these groups, H and K, both these groups have order exceeding square root of G. square root of order of G. Okay, so this corollary will help us in proving uh, the proposition which we had stated. Let us bring this. Okay, so now we want this. Finally, this was our target. So as a consequence, we have this. Okay, right. So this is clear. In the theorem, we proved order of hk equals to order of h, order of k upon order of h intersection k. And if h and k are two groups of finite group G, whose order exceeds square root of order of G, then h intersection k is non-trivial. That means it contains more elements other than also identity. And now, as a result of this, if G is a group with order PQ, where P and Q are primes, and P is the larger prime out of these two because they are distinct prime, so P is the larger prime, then the result says G has at most one subgroup of order P. વધુમાં વધુ એક સબગ્રુપ હશે P ઓર્ડરનું, કાં તો ના હોય અને કાં તો એક જ હશે. So what we do? We assume, suppose G has two subgroups of order P, then we show that they are equal. So it is at most one. So this is how we prove. So this is the first case which we usually prove. If G has no subgroup of order P, which is not possible, we are going to see. But at least let me write like this. This is not possible. Subgroup hase and exactly one subgroup it will have. Suppose G has no subgroup of order P, then we are done. Because we want to show at most one. Here we have at most one subgroup of order P. વધુમાં વધુ એક હશે, ના હોય તો we are done. But this case is not possible. I am writing this. Somebody might just see this video and think that I am doing some stupid things, which I sometimes do in my class also, in my video also. But this is not stupid. Just we are arguing right now. This is not possible. We are going to see after 2 lectures. Okay, suppose G has no subgroup order P, then we are done. And now अगर होए तो अगर होंगे तो कितना होगा? It has to be at most one, so it has to be unique. So suppose there are two subgroups of order P. So suppose H and K. Suppose if possible, H and K are subgroups of G with H and K be subgroups of G with order of H equals to order of K. Suppose both has P elements. Both have P elements. So we have more than one subgroup of order P. Then what we have to show? We show that H equals to K. So that it will be unique. Okay, we show that H equals to K. So now what about order of G? Order of G is PQ. So I write what is, so PQ is less than P square. Why? Because we are given P is greater than Q. So P is greater than Q. બંને સાઈડ P મલ્ટીપ્લાય કરો તો શું થશે? P square is greater than PQ. This is what I have written. PQ is less than P square. But what is PQ? That is, this implies order of G is less than order, so PQ, but let me write like this first. Square root PQ is less than P. Now taking root on both sides. But now what is square root PQ? So this is square root of order of G, because order of G is given to be PQ, right? This. So is less than, and what is P? P is nothing but order of H and order of K. Order of H, and this is nothing but order of K. So order of H is also greater than square root order G. Order of K is also same, which is also greater than square root order G. So by previous corollary, if we have two subgroups, this is the corollary. If you have two subgroups H and K, both has order greater than square root of order of G, then what it says, H intersection K identity, singleton identity nothing. So then, by previous corollary, what we have, H intersection K is not singleton identity. That is, order of H intersection K is not 1, or we can say that it is greater than 1, strictly greater than 1. Singleton nothing, so it has greater than 1. But we know that H intersection K is subgroup of H as well as H intersection K is subgroup of K. But H intersection K is a subgroup of both H and K. So by Lagrange's theorem, order of subgroup divides order of group. So by Lagrange's theorem, what we can say, order of H intersection K divides order of H, and order of H intersection K is also subgroup of K. So it divides order of K. So that is, both have same order, H and K. H and K are two subgroups of order P. So what we get, that is order of H intersection K divides P. P ने divide करे છે, P is a prime. So divisors of prime are 1 or P. 1 is not possible because of this case. 1 तो નથી. So that means order of H intersection K equals to 1 or P. Prime has only 2 divisors, but 1 is not possible. So that means it has to be P. So therefore, order of H intersection K is also P. But H has P elements. Order of H has P. Order of K is also P. H intersection K is obviously a subset of H. એમાં પણ P elements છે. So that means what? But H intersection K is subset of H, and order of H intersection K equals to order of H equals to P. Both has P elements, and this is subset. That means, so then we must have what is H intersection K? H intersection K equals to H, right? Because H intersection K is subset of H. H માં P elements છે. H intersection K also has P elements that we have seen now, because order cannot be 1, so it has to be P. આ બધા P elements આમાં છે. So then what is the difference? There is no element here in H which is not in H intersection K. It has P elements. All those P elements of H intersection K are here. No other element more than P elements here. So that means H intersection K equals to H, and similarly H intersection K equals to K also has P elements. So similarly we have H intersection K equals to K. So hence we can say that H equals to K. So any group of order PQ. Now this type of questions are really important in net exam. Any group of order PQ where P is a larger prime, what it says that group has at most one subgroup of that prime order. And as I said, we are going to prove that it has at least one subgroup of that prime order. At most, at least, when we join them, when we club these two results together, we get exactly one subgroup of that order. 10 order no group, exactly one subgroup of order 5. 15 order group, exactly one subgroup of order 5. 6 order group, exactly one subgroup of order 3. 6 order no group ખ્યાલ છે? Yes, what are the group of order 6? S3, we have seen, yes. And also Z6. ચેક કરજો, 3 ઓર્ડરનું એક જ સબગ્રુપ હશે. 2 ઓર્ડરના એકથી વધારે હોઈ શકે, બટ 3 ઓર્ડરનું તો એક જ સબગ્રુપ હશે. Similarly, order of group of order 14, 2 into 7. 7 is larger prime. 7 ઓર્ડરનું એક જ મળશે, exactly 1. So this is an important result. ક્યારેક ક્યારેક આવી રીતે નેટના એક્ઝામ્પલ્સમાં પણ આવા રિઝલ્ટ્સ કામ લાગે, which are just byproducts of what we are going to see in this course. So anyway, I end this lecture here. Next 2 lectures will be on normal subgroups and quotient groups, one lecture. Another one will be on homomorphism, which is most of revisions which you have seen, revision of what you have seen in the BSc, so that will go quickly. If we have any difficulty here, we can discuss in the Google Meet, and also we can discuss in the tutorial session. So I end my lecture here. Thank you.